Hello students. Today in this lecture we will be discussing about some of the basic concepts of matrix analysis of structures uh, that we will be dealing with in the formation of a matrix. Also we will be dealing with the analysis of basic matrix formed due to various displacements coordinates uh, at certain selected coordinates, and we will be analyzing the structure using matrix method approach by flexibility as well as stiffness methods. So myself Shubhranshu Jaswal, assistant professor, BBD University, Lucknow. So let us start. Now, what is the basic approach for this? Basic approach for analyzing a structure using matrix method is based upon the consistent deformation and slope deflection methods. Basically, consistent deformation and slope deflection methods are the basics of flexibility and the stiffness matrix method. In case of a flexibility matrix method, we use the basic of consistent deformation method. Also, we use the basics of conjugate beam method. Whereas in a stiffness method, we use the basics of slope deflection method. So we will be reviewing and we will be quickly brush up these two methods. So let us start with a consistent deformation method first. Um, this is a basic method where the strategy is to first of all make a structure determinate by releasing the extra internal reactions that will be making a structure indeterminate. Then after releasing the extra forces, when we get a determinate structure, the strategy would be analyzing the determinate structure using the basic equilibrium equations. So in this case, displacement compatibility of original structure equations are assembled, and then these are solved. That will help in the analysis using this method. Also, let us take an example and quickly do the question in order to understand the concept and the procedure of analyzing a structure using the consistent deformation method. For example, a propped cantilever of a span L is fixed at A and is in roller at B. Analyze it when it is subjected to a concentrated load P at the midspan. The flexural rigidity is constant throughout, that is EI is constant throughout the beam. This is a case of a propped cantilever beam. See, this is a case of a propped cantilever beam. Uh, this beam is fixed at one end. Also, a roller support is at other end. A force or a unit load of P is acting on the midspan of the beam. The length of the beam is L. So we'll start with finding out the static indeterminacy first. So in this beam, there are three internal reaction at the fixed end, one at the roller end. So total will be four. See over here, 3 plus 1, that is 4, and degree of indeterminacy, as we all know, that is the number of internal reaction minus the equilibrium condition, that is 3. So it is 1. So basically this beam is indeterminate to a degree of 1. So in order to make this beam a determinate beam, we need to remove this support reaction. Hence, we'll get a cantilever beam, and that will be a determinate structure. So by releasing the support B, that is what I just told you. By removing the support B, the vertical deflection is removed. We get a cantilever, that is a basic determinate structure. Um, so we will be analyzing to find out the reaction RB in order to find out the behavior of a structure under this vertical load. So this is a basic determinate structure. When we have removed this roller end, this is a cantilever beam, and this is a basic determinate structure. And by removing this support from the end B, under this load P, this structure will deflect like this. So the net deflection at the end B will be taken as delta 0, or we can simply say delta naught. So, and if we simply apply this reaction under we what we'll do, we'll remove this support, and we'll apply a upward reaction, that is RB, and due to this reaction RB, there will be a vertical upward deflection, and that we will be calling it as delta 1. So let us see deflection due at B due to given loading. Now given loading is load P. So deflection at B due to load P. This is a load B, or sorry, load P, and due to this load P, we'll see calculate deflection at B. So that is, obviously we know that is delta naught. So delta naught will be deflection at C plus L by 2 multiplied by slope at C. That is deflection at C plus L by 2 multiplied by slope at C. So this is deflection at C. What will be deflection over here plus L by 2 slope at C. That will give the deflection at B. So it is, we know that for slope at C will be P L cube by 3I, P L cube upon 3I. Here in this case, L is L by 2. So for a case where the end is fixed and a vertical load is applied on the in case of a cantilever beam, let us assume it as a cantilever beam where one end is fixed, other is free, and on the free end a load P is acting. We need to calculate the deflection over here. That will be PL cube upon, that will be PL cube upon 3I. Here in this case, L is L by 2, so it is PL by 2 cube upon 3I plus L by 2 PL by 2 square upon 2I. That is slope at C. We know that slope over here will be PL square upon 2I. So here again L is L by 2. So we have placed we have put the value of L as L by 2. This will give the value, that is PL cube upon 48I. This is downward. Now again we'll need to calculate the deflection at B due to redundant force RB. Now in this case, in the second case where we have applied a vertical reaction or vertical redundant force RB in the upward direction, and we need to calculate delta 1. So delta 1 again over here will be this is a simple case of a cantilever beam. Here the same case, but the difference is that this load is acting upward, so it will be RB L cube upon 3I. Same like this, RB L cube upon 3I. Here it was downward, here it is upward. So this is RB L cube upon 3I, because now here the load is RB. So instead of P, it will be RB. Now the compatibility equation says that the downward deflection due to loading for the equilibrium state, downward deflection due to loading, that should be equals to the upward deflection due to RB. So this is PL cube upon 48EI. This will be equated by this one, and that will give the value of RB is equals to P upon 16P. So in this way, we can easily calculate the extra force that was over here, and we can easily analyze the rest of the equations, the rest of the structure by using equilibrium conditions. So this method is known as consistent deformation method, and by this method we have easily calculated the support reaction that was unknown in this case. Now see, this is a basic this is the beam which we have just now analyzed, and we have calculated this reaction. This is the shear force diagram for this, and this is the bending moment diagram for this. Now there are various methods of finding deflection. Finding a deflection is also a part of the analysis of structure. Here we are analyzing, we are concerned with the analysis of indeterminate structure. So in order to find out the deflection, there are certain methods. First is a double integration method. Second is the conjugate beam method. Third is the unit load method. All these methods we have already studied in the structure analysis one part. So we will quickly consider as example of each of them, and we'll quickly brush up the concept of these three methods. First of all, there's a double integration method. We all know this equation, that is EI d2y by dx2 is equals to minus m. M is the bending moment. D2y by dx2 is the dy by dx is the slope, and whereas only y is the deflection. So by integrating this equation, we'll get by single time integrating this equation, we'll get ei dy by dx, and by double integration of this equation will give the value of y, that is deflection. So we'll see some of the standard cases, and this is the case which we have already calculated by using consistent deformation method, that is PL square upon 2 EI, PL cube upon 3 EI. These are the standard cases that we always need to remember. So in order to do the questions quickly, we need to remember the value of deflection and slopes for these standard cases. Now, for example, this is a beam. Uh, this is the beam, and for this theta b is the slope at B. This is PL square upon 2EI. In this case, this is a cantilever beam. A load P is acting on the free end, and for this case, the deflection, downward deflection at the free end B will be PL cube upon 3I. Second beam is this. This is again a cantilever beam. For this cantilever beam, a UDL of W per unit length is applied on whole span. The span is L. At the free end, we need to calculate. We need to see the slope and deflection. So theta b, that is slope at the end B, will be WL cube upon 6CI, and the deflection at the end B will be WL cube upon 8EI. Now, in this case, this is a simply supported beam. A load, a unit load, or sorry, a concentrated load of P is acting on the midspan. In this case, again, the maximum load will occur at this part under load, whereas the slope will be maximum at the ends, that is A and B. So in this case, due to symmetry, we can easily conclude that slope at A will be equal to slope at B. So we are only concerned with slope at B, that is PL square upon 16EI, and deflection at the end will be 0, because this is a hinge support. It will not allow the vertical movement of the ends. Hence, the deflection at the support will be 0. Now, in this case, again, this is a simply supported beam. It is carrying a UDL of W per unit rem on the whole span. Again, in this case, for this case, the slope at the end B, also at A, because it is a symmetrical beam, will be WL cube upon 24EI. Again, due to this vertical support, the deflection at the end will be 0. So this is how, by using simply this equation, we can find out the deflection. What we'll do, we'll consider a section at any distance x from one end, and we will calculate the moment on that section. For example, in this case, we will consider a section xx at a distance x from end A, and we'll calculate a moment at this section. The moment at this section will be calculated, and that will be substituted to the above to the equation of double integration method, and we'll simply calculate. See, in this case, the value of m will be substituted over here, and we'll get ei d2y by dx2. We'll integrate it a single time. The equation becomes EI dy by dx. That will dy by dx will give us the slope or the rotation, we can say, and will again integrate the same equation, and we'll get EI multiplied by y, that is equals to moment, and that y will give the value of deflection. So by using this equation and integrating it once and twice, we'll get the value of slope and deflection for the required beam. Now, second method is the conjugate beam method. This method is based upon the conjugate beam theorem. Conjugate beam theorem says something. There are some certain theorems that are there are in fact certain rules which are given into this theorem. Like for a conjugate beam, if for a conjugate a conjugate beam for a real beam follows certain rules. For example, if the end is hinged for a real beam, for the conjugate beam, the end will be remains hinged. For the if the end is fixed in case of a real beam, it will get free in the conjugate beam, and the free end will get fixed in the conjugate beam. If there is a internal, if there is a intermediate support, it will be converted to the internal hinge, and if there will be a internal hinge, then it will be converted into a intermediate support. So in order to calculate deflection by using this method, there are two theorems. That is, first is rotation. If we are concerned to calculate rotation at any part of a beam, we will simply draw its conjugate beam, and we'll find out the shear force onto that required point, and we that will be equals to the rotation in the original beam. Similarly, if we are concerned to of calculating a deflection at any part of a beam, then we'll draw its conjugate beam, and on the same point we'll calculate the moment, and that will be equals to the deflection in the original beam. So we'll understand it by a simple example. The example is says determine the end rotation. End rotation is the you can say the end that the end slope. End rotation in a simply supported beam of the span L, subjected to a UDL, that is uniformly distributed load W per unit length. Use conjugate beam method. So in this case, this is a beam carrying a um, uniformly distributed load over the whole span. So first of all, what we'll do, we'll quickly make its a moment diagram, and this is called the M upon EI diagram. And the conjugate beam theorem says the M upon EI diagram for the original beam is the loading diagram for the conjugate beam. I repeat, the conjugate beam theorem says that the M upon EI diagram for the original beam is the loading diagram for the conjugate beam. So in this case, if we see the both ends are hinged, so or we can say roller. So we have already seen in here that if the ends are hinged or roller, they will be remain same. So in this case also, for its conjugate beam, they will be same. Also, due to this UDL, the M upon EI diagram will be like this. It will be a parabolic, and it will be maximum at the center, and the value will be WL square upon ATI. Now, here we need to calculate the end rotation. End rotation means theta A. We can see clearly see this is a symmetrical beam. So theta A will be equals to theta B. We are concerned of finding out the end rotation. So theta A will be is equals to the shear. I told you that if we need to calculate rotation at any point of a beam, then we'll quickly make a conjugate beam of it, and at the same point we will find out the shear. So theta A will be equals to shear in the conjugate beam at A. So here is the conjugate beam. We'll calculate shear force over here, and that will be equals to the rotation over here. So due to this loading, I told you that the M upon EI diagram for the real beam will be the loading diagram for the conjugate beam. So for this beam, this will be the loading diagram. So if we are concerned to calculate shear force at A, this will be the loading diagram, and for this, due to this, the shear force at A will be RA, or we can say RA dash. So RA dash will be the half of the total load, because this load, if we see the vertical reaction equation, equilibrium equation, then sigma V, that is RA plus RB, is equals to the load of this diagram. So that is equals to half into 2 by 3 of L into WL square upon ATI. The load of this parabolic diagram will be 2 by 3 of 2 by 3 multiplied by the length, that is L, multiplied by the height, that is WL square upon ATI. So this is the uh, this will be shear force at A, and that will be equals to the rotation at A. So again, if we are concerned to calculate the moment at any point, we'll what we'll do, we'll calculate the sorry, if we concerned to calculate the deflection at any point, we'll calculate the moment on the same point in the conjugate beam, and that will be equal to the deflection at the same point. So in this case, theta I becomes WL cube upon 24 EI. And if we see, this is we have studied this before in the standard case, that was here. That was here. That is WL cube upon 24 EI. That is theta B. And same we have calculated over here. So another example, in this case, a cantilever beam is discussed. In this case, this is a fixed end, this is a free end, a load P is acting over here. So again, this is the BMD, this is the bending moment diagram, and this is the M upon EI diagram, and this will be considered as a loading diagram. This is the conjugate beam. See, I told you, for a conjugate beam, the free end becomes fixed and the fixed end becomes free. It happens over here. This is the conjugate beam, and this is the M upon EI diagram. The height of this portion is PL upon 2 EI, and the CG of this triangular loading will act as at uh, L by 3 of this span. This span is L by 2, so L by 1 by 3 upon by multiplied by L by 2 from end A, and from end C it will be 2 multiplied by L by 2 upon 3. Again, we need to determine the rotation and displacement of the free end. So rotation and displacement of the free end means we need to calculate the rotation theta B. Also, we need to calculate delta B, that is the deflection at the free end. So again, the conjugate beam theorem says theta B will be equal to shear force in the conjugate beam at B. So shear force at B will be what? Shear force at B here will be what? Shear force over here will be the total load of the conjugate beam, because it is acting, the total load of the conjugate beam is half into base into height. This is a triangular loading, so it will be half into base into height. So base is L by 2, height is PL upon 2 EI. So it is C half into PL upon 2 EI into L by 2. This is PL square upon ATI. Similarly, the other theorem says, the other part of the conjugate beam theorem says that the deflection at the end B will be is equal to the moment in the conjugate beam at B. That is, what will be the moment at B? Moment at B will be this load multiplied by the distance, perpendicular distance. The perpendicular distance will be calculated from the CG of this point to this point. This portion is L by 2, and the CG over here will be 2 by 3 of L by 2. So 2 by 3 of L by 2 plus L by 2 multiplied by the load of this triangle that we have just calculated over here. So in this case, again, this is that is PL square upon ATI multiplied by the uh, uh, L minus 1 upon 3 of L by 2. This will give the value of PL cube upon 48 EI. Now, next method is the unit load method. This method is also again used to calculate the deflection or rotation at any point in case of a beam. In this case, we need the required displacement is in terms of capital M multiplied by small m dx upon EI. This is the integration, and the capital M is due to the present loading, and small m is capital M is the moment due to the present loading. Small m is the moment due to the unit load applied. So we'll quickly see. In this case, determine the rotation and deflection at the free end of a cantilever beam of a span L subjected to a UDL over the entire span. See, this is a case cantilever beam. The UDL W is applied on the entire span. So what we'll do, in order to put the value, we'll calculate M. M is the moment at any section due to the present loading. Capital M is the moment at any section due to the present loading. So present loading is W. So we'll calculate moment at any section, that will be W multiplied by X multiplied by the distance, that is X by 2. So it will be W X square by 2. This is the moment, W X square by 2. The small m is, I told you that due to the moment due to the unit load. So we'll consider a unit load uh, in this beam. So unit load, due to this unit load, if the load is 1, the moment will be, we'll simply put the value over here, and to find the rotation at the free end, a unit load is applied. Due to this unit load, M will be 1 throughout, because when the load becomes 1, the value will become 1. So in this way, theta, the equation for theta will be 0 to L. L is the span. 0 to L, limit goes from 0 to L, but means it will be calculated from this part to this part. So it is 0 to L. Capital M, M, small m, dx upon EI will put the value. The capital M is calculated as Wx square by 2, and the small m is 1. The EI is constant throughout, and the equation becomes like this. This will be integrated to get the value of small w upon 2 EI, x cube upon 3, limit 0 to L. And by solving this part, the value comes WL cube upon 6 EI. This is how we have calculated the rotation at the end. So again, for the same equation, if we need to calculate the deflection, again, M is equals to deflection will be the same part. This is how we can calculate the deflection. Deflection will be a moment multiplied by the perpendicular distance. That is over here, that is moment multiplied by perpendicular distance. So small m, due to unit load, unit load is 1 multiplied by x, that is x. See here, for a unit rotation, for a unit load, uh, for rotation we have applied a unit rotation, and this has given the value of 1 throughout. This is what we have written over here. And for the deflection, we have applied a unit force at the end, and this will give at any section value of 1 multiplied by x. If the value of x is 1, then the value of the moment at the point will be 1. If the value of x is 2, the moment at that point due to unit load will be 2. If the value of x is 3, the moment due to unit load at the same point will be 3. So it depends upon the value of x. So small m will be 1 multiplied by x, that is x. So and also this will give delta is equals to 0 to L m x dx upon ei. Remember, in the slope equation it was capital M multiplied by small m dx upon ei, and in this case it is capital M x dx upon ei. So this is the value of again we have calculated the value, and that is wx square upon 2 multiplied by x. This is x is this thing mx and 1 upon ei dx. Or integrating this part, we'll get this equation, and on solving this equation we'll get the value of wl4 upon ati. And this was again a standard case, so you can see and calculate and compare it with the previous part of a standard cases, that is wl4 upon ati for a cantilever beam carrying a udl on the whole span. See, in this it is a case over here for a cantilever beam carrying a UDL on the whole span. It is WL cube upon ATI. That is the deflection, and WL cube upon 6CI was the slope or the rotation. That's what we have calculated in this question. That is WL cube upon 6CI. This is the rotation, and WL4 upon ATI was the deflection. So this is how we can easily calculate the deflection for the standard cases. In this lecture we have quickly discussed the basics of 3 cases of finding the deflection in case of indeterminate beams. First was double integration method. Second was conjugate beam method, and the third was unit load method. Double integration method is also known as the Macaulay's method because the equation is same. We just need to integrate it once to get the value of slope or the rotation, and we need to integrate it twice to get the value of deflection. Remember, on integrating the equation by using double integration method, also some of the constant, for example C1 or C2 comes due to the integration part, and we need to solve the and calculate the C1, the value of C1 and C2 by applying the boundary condition. For example, boundary condition for this beam will be one of the boundary end condition says that we can clearly see that there will be no deflection at this part. So at this end A, the deflection will be 0. So at end A, where the L is 0, the deflection will be 0. Also at this part, if we see a cantilever beam like this, if we see a cantilever beam like this, then at the free end there will be deflection, but at this end there will be no deflection. So boundary condition says that deflection at this end will be 0, and deflection at this end will be certain value. So by applying the boundary condition, we will be easily able to calculate uh, uh, the integration constant, that is C1 C2, and we'll get the final equation of deflection as well as slope for this for the standard cases. So this is how we can easily calculate all these things, and this was the basic approach for finding the deflections using these methods. And finding deflection is a part of analysis. In the upcoming lectures, we'll be discussing about the application of all these methods into the matrix analysis of structures. So hope this lecture would have been beneficial for you. So thank you, class.